last episode, I mentioned that there are other two-level systems, except photons with their polarization. Two-level systems are good because they allow us to implement qubits. So let's learn more about them. In 1922, German physicists Otto Stern and Walter Gerlach conducted an experiment, which is now known as the Stern-Gerlach experiment. They used a narrow directed beam of particles, silver atoms, which was passing through the apparatus where they were exposed to the magnetic field, oriented orthogonally to the particle's propagation. The direction of magnetic field orientation is important to us, so let's call it Z. The silver atoms fly along the axis Y, and the field is oriented along the axis Z. After passing the magnetic field, particles' positions were detected on the screen placed after the apparatus. The experiment was expected to show how electrons in silver atoms interact with the magnetic field and is this interaction quantized. The detection screen showed that silver atoms do interact with magnetic field, but in a very strange way. About 1/2 of atoms deflect by a constant angle to the upper part of the screen, while another half deflect by the same angle to the lower part of the screen. This result is indeed important. It shows that atoms have some measurable property that can seriously alter their behavior in the presence of magnetic fields. This property was called the magnetic moment of a particle, or spin. The name spin here suggests that something is spinning. Electrons are charged particles, and in Bohr's model of an atom, they circulate around the positive core producing magnetic field. The direction of this field depends on the direction and the trajectory of this rotation. And it is very hard to believe that all electrons in all silver atoms from the beam rotated in just one plane. So in the terms of Bohr's atom with rotating electrons, this experimental result has no explanation. So instead of imagining the electrons as some charged rotating balls, we need to admit that we don't know what they are. But we know that they interact with magnetic fields in this strange way. When something inexplicable like this happens, physicists don't complain, they research. And how can we research this? Well, first we need to build more Stern-Gerlach apparatus. And we will place them one after another. The thing we are going to adjust in these different apparatus is the direction of the magnetic field. In the first experiment, we are going to place two identical apparatus one after another. The first apparatus splits the initial beam of silver atoms into parts. Let's call them Z plus and Z minus. Z plus are those particles that deflect up along the axis Z, and Z minus those which go down the axis Z. And we will block the Z minus part of the beam, allowing only Z plus to enter the second apparatus. This experiment shows that all particles from the Z plus part of the beam deflect to the upper direction in the second apparatus. And the angle of deflection is the same as in the first set. And of course, if we allow only Z minus beam enter the second apparatus, all the particles from that beam deflect down again. This follows just from the symmetry of this experimental set. Okay, Now, what if we orient the second Stern-Gerlach apparatus along the x-axis? How the z plus particles will react to this new orientation of the field? Well, the result is this. They again interact with the field and form two equal beams with the same constant angle of deflection. Well, we are experienced enough to see here all properties of a measurement process of a two-level system. First, we have two possible easily distinguishable measurement results. Second, for a particular particle, these results are truly random. Third, after the measurement, the particle changes its state to that being obtained by measurement and stays in this state in the sequential measurements. 4. Measurements in different bases give us independent results. The last property does not have to be always true, at least not for all base pairs. Okay, we have a two-level system. This means we can draw it on the Bloch sphere. The state of the particles with the spin up along the z-axis we will denote 0 and place it at the top of the sphere. In the opposite point situates the state 1, which is spin-down particles along the z-axis. These two states constitute the basis, which defines the spin measurement along the z-axis. X-axis has the angle of pi divided by 2 with the z-axis, and we will place here our states for spin up and spin down along the x-axis. These states we will call plus and minus, and they constitute the basis for measurement of the spin along the x-axis. And the states of the particles having spin up and spin down along the y-axis, which is, as you remember, the direction of their propagation, are no surprise on the y-axis, forming the rotational basis. However, I am not sure that the term rotational has physical meaning here. Probably no, it does not. But it is an analog of the rotational basis for photons. That's why I called it this way. Okay. Particles that have this kind of measurement results in the Stern-Gerlach experiment, just two measurement outcomes, are called spin 1/2 particles. And they represent a perfectly defined two-level systems for us.